Erwin Schrödinger's story begins in the late 19th century, in a world where science was evolving at an extraordinary pace. The Industrial Revolution had reshaped society, the mysteries of electricity and magnetism were being uncovered, and the boundaries of classical physics were being pushed to their limits. In this vibrant intellectual climate, a young boy was born in Vienna in 1887, Erwin Rudolf Joseph Alexander Schrödinger, destined to challenge the very foundations of how humanity understood reality itself. From his earliest years, Schrödinger showed signs of an unusually curious mind. The son of a botanist and a cultured mother, he grew up in a household filled with books, art, and scientific discussion. His father, Rudolf Schrödinger, was a man deeply interested in the natural sciences and often engaged his son in experiments and demonstrations at home. These early encounters did not just spark Erwin's curiosity, they nurtured in him a deep appreciation for both observation and reasoning, the twin pillars of scientific thought. As a child, Schrödinger was not content merely to observe the world around him. He wanted to understand it. He would spend hours studying the patterns of nature, the fall of light on a surface, the symmetry of leaves, the behavior of shadows on walls. Even before formal schooling shaped his intellect, he possessed an instinctive sense of order and pattern, qualities that would later define his scientific approach. He was fascinated by how numbers could describe the world, how mathematical relationships could reveal truths that human eyes could not see. Mathematics, for him, was not simply a subject to be learned. It was a language through which the universe spoke. When Schrödinger entered school, his brilliance quickly became evident. His teachers noticed his exceptional ability to grasp complex ideas and his passion for both the precision of mathematics and the wonder of physics. While most students memorized formulas, Schrödinger asked why those formulas worked. He wanted to dig beneath the surface, to uncover the principles that made the universe function. This relentless curiosity distinguished him from others and hinted at the revolutionary thinker he would become. His education in Vienna was rich with exposure to the intellectual traditions of both science and philosophy, and it was this combination that allowed his mind to expand beyond the limits of conventional thinking. Vienna at the turn of the century was not just a city, it was a cultural and intellectual epicenter. Artists, philosophers, and scientists gathered in cafes and universities, exchanging ideas that would define modern thought. In such an environment, Schrödinger was immersed in discussions about logic, truth, and the nature of existence. He read deeply into both Western and Eastern philosophies, contemplating how abstract ideas of reality could align with scientific discoveries. These reflections were not distractions from his studies, they were the roots of his intellectual identity. He began to see science not merely as a collection of experiments and equations, but as a profound quest to understand the ultimate structure of reality. In his teenage years, Schrödinger's fascination with mathematics deepened. He began to explore how mathematical patterns could explain natural phenomena. Geometry, calculus, and algebra were not for him just academic exercises. They were windows into the unseen. He was intrigued by the harmony between mathematical symbols and physical reality, and he often found beauty in the precision of equations. His notebooks were filled with sketches of ideas, calculations, and theoretical reflections that blended science and philosophy. To him, mathematics was poetry written in numbers, and physics was its melody. When he entered the University of Vienna in 1906, Schrödinger encountered an academic world dominated by classical physics. The laws of Newton still reigned supreme, and the universe was viewed as a vast, predictable machine operating under deterministic laws. But beneath this confident framework, cracks were beginning to appear. Experiments on radiation, light, and atomic behavior were revealing strange inconsistencies that classical theory could not explain. Schrödinger was drawn to these mysteries. He studied under distinguished physicists such as Friedrich Hesse-Hurrell, who had worked with concepts related to energy and radiation. Under their guidance, Schrödinger developed a disciplined approach to problem solving, but he also began to question the rigid boundaries of classical thought. His fascination with wave phenomena began during these years. The study of sound waves, light waves, and electromagnetic theory captivated him. He saw in waves a universal principle, a continuous, harmonious motion that could connect the smallest particles to the grandest cosmic structures. This early interest planted the seed for his later revolutionary insight that particles themselves might behave like waves. But that revelation was still years away. For now, Schrödinger was absorbing everything around him, blending mathematical precision with philosophical depth, and allowing his mind to wander freely across the landscape of ideas. Schrödinger's student years were marked by intense study, but also by an inner search for meaning. He was not satisfied with surface-level understanding. He wanted to know the why behind every phenomenon. Why did light behave both as a wave and as a particle? Why did nature follow mathematical laws at all? These were not questions of mere curiosity. They were questions of worldview, and they drove Schrödinger toward a more unified vision of science. He began to see that the separation between physics and philosophy was artificial. Both sought the same truth, only through different languages. This realization would later shape the poetic tone of his scientific writings and his willingness to challenge rigid boundaries in thought. During his time at the university, Schrödinger also developed a strong appreciation for experimental science. Even though his greatest strength lay in theory, he participated in laboratory work, observing how physical laws manifested in measurable ways. Yet, he sensed that beneath every experiment was a deeper, hidden order, one that mathematics alone could describe. This conviction grew stronger as he studied the works of great physicists such as James Clerk Maxwell, Ludwig Boltzmann, and Hermann von Helmholtz. Maxwell's equations showed him how mathematical harmony could describe electromagnetic fields with astonishing accuracy. Boltzmann's work on statistical mechanics inspired him to think about the probabilistic nature of reality. These influences shaped his intellectual DNA and prepared him for the coming quantum revolution. It was Boltzmann's approach, in particular, that left a lasting mark on Schrödinger's mind. Boltzmann had introduced the idea that the behavior of matter on a microscopic scale could only be understood statistically through probabilities. This idea was unsettling to many physicists of the time who were comfortable with deterministic laws. But Schrödinger was intrigued. He saw in Boltzmann's statistical mechanics a doorway to a new way of thinking, a way that embraced uncertainty and complexity rather than rejecting it. This willingness to accept ambiguity would later allow Schrödinger to grasp the essence of quantum theory when others resisted it. By the time he completed his doctoral studies in 1910, Schrödinger had already developed a reputation for brilliance. His doctoral dissertation, focused on the conduction of electricity on the surface of insulators, was technical but showed the clarity of his analytical mind. Yet, his interests extended far beyond the confines of any single topic. He was equally at home discussing pure mathematics, thermodynamics, or the philosophical implications of physical laws. His mind worked like a web, connecting diverse ideas into a unified whole. This ability to synthesize different domains of knowledge would become his greatest strength as a scientist. The outbreak of the First World War in 1914 disrupted Schrödinger's early career, but even during those years of turmoil, he continued to think deeply about science and philosophy. Serving as an artillery officer, he spent long nights contemplating the mathematical beauty of the natural world, even as the chaos of war unfolded around him. The contrast between destruction and intellectual pursuit deepened his understanding of the fragility and mystery of life. These reflections shaped his later writings, where he would often connect physics with questions about consciousness and existence. War taught him that the universe was not merely a mechanism to be analyzed, but a living mystery to be experienced. After the war, Schrödinger returned to academic life with renewed determination. The scientific world was changing rapidly. Experiments in atomic physics were producing results that defied classical explanations. Max Planck had introduced the concept of energy quanta, and Albert Einstein had expanded it to explain the photoelectric effect, suggesting that light itself came in packets of energy called photons. Niels Bohr had proposed his atomic model, in which electrons occupied discrete energy levels. These were radical ideas that challenged centuries of deterministic thinking. Schrödinger, with his mathematical skill and philosophical open-mindedness, was uniquely prepared to explore this new frontier. But long before he would develop his famous wave equation, Schrödinger's thinking had been shaped by the deep foundations laid in his youth. His fascination with mathematics, his love for the patterns of nature, and his ability to see connections where others saw divisions. His early life had taught him that true understanding requires both logic and imagination, both calculation and contemplation. He viewed the universe not as a cold machine, but as a living symphony of form and motion, guided by laws that could be expressed through the elegant language of mathematics. This worldview would eventually lead him to reinterpret the nature of matter itself. Schrödinger's fascination with mathematics gave him not only a tool, but a lens through which to perceive the world. Every equation he encountered was, for him, a reflection of something deeper, a correspondence between thought and reality. Mathematics became a bridge between the human mind and the cosmos. This belief, rooted in his early education, shaped every discovery he later made. He learned that behind every scientific law lies a pattern, and behind every pattern lies meaning. His early years of exploring geometry, algebra, and calculus were more than academic exercises. They were steps on a lifelong journey to uncover the hidden structure of existence. As he matured intellectually, Schrödinger began to see the relationship between mathematics and physics as a dialogue rather than a hierarchy. Mathematics provided the symbols and structure, while physics gave those symbols physical meaning. His curiosity was not confined to the known, it reached into the possible. He once remarked that the task of science was not to collect facts, but to construct a coherent picture of reality. This perspective, nurtured in his early years, would become the philosophical core of his scientific career. He found joy in theoretical beauty, often saying that equations must not only be correct, but aesthetically satisfying. This artistic sensibility set him apart from many of his contemporaries. To Schrödinger, beauty was a sign of truth. If a mathematical model was elegant and harmonious, it likely revealed something real about nature. This intuition would guide him decades later when he formulated his wave equation, an achievement that combined precision, creativity, and aesthetic simplicity. By the end of his early academic period, Schrödinger had absorbed a vast range of ideas: classical mechanics, thermodynamics, wave theory, and the beginnings of quantum thought. Yet, more importantly, he had developed a mindset that refused to be constrained by dogma. He had learned to think freely, to question assumptions, and to find unity in diversity. His early fascination with mathematics and physics was not just the story of a young man learning science, it was the story of a mind awakening to the profound harmony between reason and reality. Every equation he studied, every question he asked, was a step toward the moment when he would transform human understanding of the microscopic world forever. As Erwin Schrödinger entered his mature years, the seeds planted in his early fascination with mathematics and physics began to bear fruit in unexpected ways. The same curiosity that once drove him to trace the path of light across a wall or calculate the geometry of a leaf's curve was now guiding him through the labyrinth of quantum uncertainty. The habits of mind he had developed in childhood, the precision of mathematical reasoning, the aesthetic sense of symmetry, and the philosophical yearning to find unity, were now the compass by which he navigated one of the greatest intellectual revolutions in history. When the First World War ended and Europe tried to rebuild itself, Schrödinger returned to academic life with an intensity sharpened by years of reflection. He took teaching positions at various universities, Jena, Stuttgart, Breslau, Zurich, and everywhere he went, he carried the same sense of wonder that had animated him since youth. Students and colleagues quickly realized that he was not an ordinary professor who merely explained formulas. He spoke of equations as if they were living entities, as if each symbol contained a secret pulse of the universe. His lectures were a blend of logic and poetry, of rigor and imagination, where mathematical derivations intertwined with philosophical musings. Many found it bewildering, others inspiring, but all recognized that Schrödinger saw the world differently. His fascination with the mathematical description of nature deepened as he explored the latest developments in atomic theory. Max Planck's quantum hypothesis and Niels Bohr's atomic model had introduced strange new ideas about the discontinuity of energy. These theories suggested that at microscopic scales, the universe behaved not as a smooth continuum, but in jumps, quanta, and probabilities. To a mind raised in the symmetry of mathematics and the continuous flow of waves, this new, quantum world seemed incomplete, even disturbing. Yet Schrödinger was not dismissive, he was curious. His early training in mathematics had taught him that apparent contradictions often conceal deeper harmony. He suspected that beneath the irregular quantum behavior there might lie a unifying principle waiting to be uncovered. He began to study the works of Louis de Broglie, a young French physicist who had proposed a daring idea. Particles like electrons might also possess wave-like properties. This suggestion resonated deeply with Schrödinger. It matched the intuition that had grown in him since his youth, that waves represented the natural language of the universe. To him, it was almost poetic that the smallest pieces of matter could also move in graceful undulations, echoing the same mathematical forms that described light and sound. His fascination with wave mathematics, nurtured through years of studying oscillations and differential equations, now met its destiny in the realm of quantum theory. During his stay in Zurich around 1925, Schrödinger began what would become one of the most productive periods of his life. He withdrew from the distractions of social life and immersed himself in a world of symbols, integrals, and physical intuition. His small apartment became both laboratory and sanctuary, where chalk dust mixed with coffee aroma and pages of calculations filled every surface. He sought a mathematical equation that could describe the wave behavior of particles, one that would make sense of the strange patterns seen in atomic spectra. His approach was guided entirely by the principles he had internalized as a young mathematician: clarity, harmony, and universality. The result of that solitary quest was the equation that now bears his name. With the simplicity of genius, Schrödinger translated de Broglie's concept into a precise mathematical form, the Schrödinger equation, an expression that described how the wave function of a particle evolved over time. It was a fusion of mathematics and physics so natural that it seemed inevitable in hindsight, yet it required the kind of intuitive leap only a mind trained in both rigor and imagination could make. When he first tested the equation on the hydrogen atom, it produced the exact energy levels that Bohr's model had predicted from a completely different starting point. In that moment, Schrödinger realized he had discovered not just an equation, but a universal law of motion for the quantum realm. His achievement was not merely technical. It was the culmination of everything his early intellectual life had prepared him for. The beauty of the wave equation lay in its continuity. It restored a sense of smoothness and order to a world that had seemed fragmented by quantum jumps. Where others saw chaos, Schrödinger saw music, the rhythm of existence expressed in a mathematical score. His love for the unity of mathematics and nature had led him to a theory that unified the particle and the wave, determinism and probability, the measurable and the mysterious. When he published his series of papers on wave mechanics in 1926, the scientific community was astonished. Within months, his work transformed theoretical physics. Even Albert Einstein, who admired few, praised Schrödinger's formulation as an achievement of rare beauty. But the equation also raised profound questions. What was the physical meaning of the wave function? Did it describe a real wave in space, or merely a mathematical abstraction of probability? These questions reignited Schrödinger's philosophical side, the same side that had once pondered geometry and metaphysics as a schoolboy. He believed the wave function represented something real, a continuous field that carried the essence of matter. For him, mathematics was not just a tool to predict outcomes, it was a mirror reflecting reality itself. The debates that followed between Schrödinger and other quantum pioneers, such as Bohr and Heisenberg, echoed his lifelong intellectual struggle. The tension between certainty and uncertainty, between mathematics as truth and mathematics as description. Bohr's interpretation of quantum mechanics emphasized indeterminacy and the role of observation. Schrödinger found this deeply unsatisfying. His early education had taught him that the universe operated through intelligible order, not pure randomness. Thus, when he created the famous thought experiment of Schrödinger's cat, it was more than a playful metaphor. It was a protest against what he saw as the abandonment of realism. His cat, suspended between life and death, was a symbol of the absurdity he felt in the idea that reality could depend solely on measurement. To understand why Schrödinger fought so passionately for a rational, continuous interpretation of quantum mechanics, one must return again to his childhood lessons. The Vienna of his youth had instilled in him an aesthetic respect for order and pattern, drawn from both art and science. To him, the universe was like a great architectural structure, intricate, but never arbitrary. The mathematics he loved was not chaos disguised as calculation, it was harmony given form. Every theorem, every equation, carried moral as well as intellectual weight. He often said that the scientist's task was not merely to calculate, but to comprehend. This conviction explains why he resisted any theory that reduced the universe to randomness or observation. Yet, even in disagreement, Schrödinger's influence was immense. His wave mechanics became the foundation for the modern quantum framework. Every branch of physics, from chemistry to solid-state electronics to quantum computing, rests upon principles that trace back to his early insight into the unity of mathematics and physical law. The quantum world that once seemed disordered became navigable through his equations. In a sense, he brought music to the microscopic, giving scientists a score by which to read the vibrations of atoms and molecules. His early fascination with mathematics had matured into a global language for the invisible. Beyond physics, Schrödinger's curiosity continued to expand. He turned his mathematical gaze toward biology and philosophy, searching for universal patterns that transcended disciplines. In his later book, What is Life?, he argued that living systems must contain a kind of a periodic crystal, a structure capable of carrying genetic information with stability and variation, an idea that directly inspired the discovery of the DNA double helix years later. The same love for mathematical structure that had once driven him to describe electrons now guided him to understand life itself. The continuity of his thinking is striking. From waves to genes, from quantum states to living organisms, he sought the same underlying order. Throughout his life, Schrödinger's personal reflections revealed how deeply intertwined his scientific work was with his philosophical beliefs. He often wrote about the unity of consciousness and the illusion of separateness, ideas drawn from both Western philosophy and the Vedantic traditions of India. His study of these ideas was not mere spiritual curiosity, it was a continuation of his lifelong pursuit of unity. Just as mathematics revealed the hidden coherence of nature, he believed that consciousness revealed the hidden coherence of being. This outlook gave his scientific work a depth that went beyond calculation. It became a meditation on existence itself. His colleagues sometimes found his philosophical writings perplexing, yet they could not deny the brilliance behind them. Schrödinger moved effortlessly between the worlds of logic and metaphysics, as if the boundary between them were an illusion. This intellectual fluidity had been part of him since childhood, when he saw no contradiction between solving equations and pondering the meaning of life. His fascination with mathematics and physics had always been about more than numbers. It was about the search for truth. And truth, for Schrödinger, was never divided into compartments. In his later years, as he reflected on his journey, Schrödinger often spoke of beauty as the guiding force of his discoveries. He said that the ultimate test of any scientific theory was not only its accuracy but its elegance. This conviction traces directly back to the sensibilities he developed in his youth, when mathematical forms first revealed their harmony to him. He saw in beauty a sign of alignment between human thought and cosmic order. In this sense, his early fascination had matured into a philosophy of science, one that continues to influence physicists to this day. The impact of Schrödinger's early intellectual development cannot be overstated. Without his training in mathematics, he might never have found the courage to express the quantum world through equations. Without his philosophical curiosity, he might never have dared to interpret those equations as reflections of reality rather than mere tools. His revolutionary thinking was not born suddenly in 1926. It was the flowering of decades of curiosity, nurtured by a deep love of both reasoning and wonder. When future generations study Schrödinger's legacy, they often focus on the cat, the equation, or the debates with Bohr. But the true story lies in the mind that created them, a mind shaped by early fascination, disciplined by mathematics, inspired by physics, and elevated by philosophy. The young boy who once marveled at the patterns of nature became the man who revealed that nature itself is pattern, written in waves of probability and governed by equations of timeless beauty. His life is a reminder that science is not merely the accumulation of data, but the continuation of a human dream, the dream of understanding. Even today, when physicists manipulate quantum states and build quantum computers, they are, in a sense, speaking the language that Schrödinger first imagined. His mathematical intuition continues to guide the technology that defines modern civilization. The lasers that read our disks, the semiconductors that power our devices, the algorithms that process our data, all rest upon principles first expressed through his wave mechanics. In this way, his childhood fascination with numbers and forces has rippled outward across a century, shaping the material and intellectual landscape of our world. As the camera of history pans back from the laboratory to the cosmos, one can see Schrödinger's contribution not as an isolated discovery, but as a continuation of humanity's oldest quest to find order amid mystery. From the stars above to the atoms within, he taught us that reality, however strange, follows patterns that can be traced and understood. And yet, he also reminded us that understanding is not the end of wonder, it is its beginning. When Schrödinger passed away in 1961, the world lost not only a scientist but a philosopher of nature, a mathematician of existence. His journey from a curious Viennese boy to the architect of quantum theory is a testament to the power of fascination, the kind that begins in childhood and never fades. His story reveals how the smallest spark of curiosity can illuminate the darkest corners of reality, and how mathematics, when guided by imagination, becomes more than a tool. It becomes a bridge between mind and universe. The echoes of his genius still resonate wherever science seeks to uncover the invisible. Every time a student learns the Schrödinger equation, every time a researcher speaks of wave functions or probability amplitudes, the spirit of that early fascination lives on. It reminds us that the heart of discovery lies not in instruments or laboratories, but in the human desire to understand, to connect, to find beauty in the logic of the world. Erwin Schrödinger's early fascination with mathematics and physics did more than shape his thinking. It shaped the course of modern science. From the quiet classrooms of Vienna to the quantum laboratories of today, his influence endures as a melody of reason and imagination, resonating across time. In the rhythm of his equations and the paradox of his cat, we find the reflection of a single truth that curiosity, when guided by wonder and discipline, can transform not only our knowledge of the universe, but our understanding of ourselves. In the early decades of the 20th century, the world of physics stood at a crossroads. The elegant certainty of Newtonian mechanics, which had guided scientists for centuries, was beginning to crumble under the weight of new discoveries. The old vision of the universe as a perfectly predictable machine was being challenged by strange phenomena emerging from the study of atoms and radiation. At the heart of this scientific upheaval stood Erwin Schrödinger, a man whose work would transform the chaos of the quantum world into a new and harmonious language known as wave mechanics. His ideas did not merely solve equations, they reshaped the philosophical structure of science itself, changing forever how humanity understood reality. Schrödinger's journey toward wave mechanics began long before he ever wrote his famous equation. It was the culmination of years of curiosity, frustration, and relentless searching for meaning within the mysteries of quantum behavior. When he began his professional career, the landscape of physics was dominated by uncertainty. Max Planck had introduced the idea that energy comes in discrete packets, or quanta, in 1900. Albert Einstein in 1905 expanded this concept to light, suggesting that it behaved both as a wave and as a stream of particles called photons. Niels Bohr then built his atomic model, describing electrons orbiting a nucleus in quantized shells. These ideas were revolutionary, but they were also incomplete. They offered mathematical success without intuitive understanding. To Schrödinger, who valued beauty and coherence in science, this was unsatisfactory. By the early 1920s, quantum theory had become a puzzle with many missing pieces. Experiments confirmed that energy levels in atoms were quantized, but the underlying reason remained mysterious. Physicists such as Werner Heisenberg, Max Born, and others were developing new mathematical techniques to describe atomic behavior, but their approach, matrix mechanics, felt abstract and detached from physical reality. Schrödinger, steeped in the traditions of classical physics and the beauty of continuous mathematics, sought something different. He wanted a theory that could describe the atomic world not as a collection of random events, but as a structured, flowing system, much like the waves that governed light and sound. The turning point came in 1924 when Schrödinger encountered the doctoral thesis of a young French physicist, Louis de Broglie. De Broglie had proposed a radical idea that all particles, including electrons, might have wave-like properties. He suggested that just as light could behave both as a wave and a particle, matter too might possess a dual nature. The equation he proposed related a particle's momentum to its wavelength, implying that the microscopic world was filled with matter waves. This concept struck Schrödinger like a revelation. It was elegant, simple, and harmonized perfectly with his lifelong fascination for the unity of mathematics and nature. To a mind like Schrödinger's, the idea that particles could be described as waves was more than a theory. It was a poetic truth. He saw in de Broglie's hypothesis the possibility of restoring continuity and determinism to the strange world of quanta. The image of electrons moving not as discrete points but as vibrating waves resonated deeply with his aesthetic sense of order. He began to wonder if there might exist a single equation, a mathematical description, that could express how these matter waves evolve and interact. For months, he withdrew into a period of intense work, isolating himself in the peaceful surroundings of the Swiss Alps, where he could think without distraction. It was during this time of seclusion, in the winter of 1925-1926, that Schrödinger conceived his revolutionary idea. Drawing inspiration from classical wave equations that described the vibration of strings and the propagation of sound or light, he sought to build an analogous framework for particles. He imagined a wave function, a mathematical entity that would describe the state of a particle in space and time. But unlike the physical waves of sound or light, this new wave was not something tangible. It represented the probability of where a particle might be found. Schrödinger's genius lay in translating this concept into precise mathematics. Working tirelessly, he derived a differential equation that expressed how the wave function changes with time and space. It was an equation of extraordinary simplicity and power, linking energy, momentum, and position in a continuous framework. When he applied it to the hydrogen atom, a system that had long defied complete explanation, The results were astonishing. The equation predicted exactly the same energy levels that Bohr's earlier, semi-classical model had described, but now they emerged naturally from pure mathematics. Schrödinger had done what no one else had achieved. He had built a theory that explained quantum phenomena through the logic of waves. The discovery electrified the scientific world. In 1926, Schrödinger published a series of 4 papers in the Annalen der Physik, introducing what he called wave mechanics. Each paper was a masterpiece of clarity and insight. The first presented the fundamental equation itself. The second showed how it could describe the structure of atoms. The third connected it to the existing quantum rules, and the fourth extended it to more complex systems. For the first time, scientists had a coherent and mathematically elegant description of the microscopic world. Where Heisenberg's matrix mechanics seemed opaque, Schrödinger's waves were intuitive and visualizable. Physicists could now picture electrons not as planets orbiting a sun, but as standing waves confined within atomic boundaries, each with its own unique vibration pattern. The reaction was immediate and profound. Many physicists, including Albert Einstein, welcomed Schrödinger's formulation as a return to the physical reality they longed for. Einstein famously wrote to him, saying that the theory was beautiful beyond compare. Schrödinger himself felt a deep satisfaction, not only because his work explained experimental results, but because it embodied the aesthetic harmony he had always sought in science. He believed that truth in physics must be both mathematically consistent and philosophically satisfying, and his wave mechanics seemed to achieve both. However, as with all great ideas, the implications of Schrödinger's theory were not without controversy. His equation introduced the wave function, denoted by the Greek letter psi, as the central quantity of quantum theory. But what exactly did represent? Schrödinger initially interpreted it as a real physical wave, a continuous oscillation in space that somehow guided the motion of particles. He imagined that matter was spread out like a mist or vibration filling space. This view was comforting because it maintained a sense of determinism. The evolution of T followed precise mathematical rules, leaving no room for randomness. But not all of Schrödinger's contemporaries agreed. Max Born proposed a different interpretation, that the wave function did not represent a real wave, but a probability amplitude, the likelihood of finding a particle in a given place. This probabilistic view, later formalized in what became known as the Copenhagen interpretation, conflicted with Schrödinger's deterministic instincts. He resisted the idea that nature was governed by chance. To him, the universe was an orderly system governed by mathematical laws, not by randomness or observation. The debates that followed between Schrödinger, Bohr, and Heisenberg would define the philosophical foundations of quantum mechanics for decades to come. Still, the power of Schrödinger's wave mechanics could not be denied. It worked. The equation predicted phenomena across chemistry, atomic structure, and spectroscopy with astonishing accuracy. It allowed scientists to compute the behavior of electrons in molecules, to understand the emission and absorption of light, and to build the groundwork for technologies that would later define the modern world. Wave mechanics became one of the twin pillars of quantum theory, standing alongside Heisenberg's matrix formulation. Eventually, Paul Dirac would demonstrate that the two approaches were mathematically equivalent, different languages describing the same underlying reality. Yet, it was Schrödinger's version that captured the imagination of generations to come, because it gave quantum physics a face, waves, patterns, vibrations, something humans could visualize. To appreciate the revolutionary impact of Schrödinger's work, one must remember the intellectual courage it required. In proposing wave mechanics, he had challenged the prevailing notions of what matter and energy were. The concept that a particle could be described by a mathematical wave function went against centuries of intuition. But Schrödinger's belief in the unity of mathematics and nature gave him the confidence to follow his reasoning wherever it led. His work demonstrated that the universe at its most fundamental level is not composed of tiny, solid balls, but of mathematical forms, vibrations of probability, ripples in an abstract sea of possibilities. The elegance of Schrödinger's equation also reflected his personality. He approached physics not as a cold engineer of formulas, but as an artist of thought. For him, the process of discovery was an act of creation, where intuition guided calculation. He once remarked that the purpose of science was not merely to predict outcomes, but to reveal harmony. In this sense, wave mechanics was both a scientific and a philosophical triumph. It restored a sense of beauty to a world that quantum uncertainty had rendered chaotic. Schrödinger's derivation of the equation was not an accident of algebra, but a synthesis of insight, training, and aesthetic judgment. His deep familiarity with classical mechanics and wave theory allowed him to translate physical intuition into mathematical expression with remarkable fluency. He understood that the universe could be described by patterns of motion, oscillations, frequencies, and amplitudes, and that these patterns could bridge the gap between the visible and the invisible. In the ripples of his equations, he heard the music of the cosmos. His work also revealed something profound about the nature of scientific progress. Great revolutions in science often occur not through the discovery of new facts, but through new ways of seeing old ones. Schrödinger's genius lay in his ability to reimagine the familiar: electrons, atoms, light, not as isolated entities but as interconnected waves of existence. His wave mechanics unified what had seemed fragmented, offering a single conceptual framework for understanding the microscopic world. It was a moment when science regained its narrative coherence, and Schrödinger, with his poet's soul and mathematician's precision, became its storyteller. In the months following his discovery, Schrödinger was invited to lecture across Europe. His calm voice and deliberate explanations captivated audiences. He spoke not just as a physicist but as a philosopher, emphasizing that the new quantum theory was not merely a set of equations, but a new way of thinking about reality itself. The success of wave mechanics elevated him to international fame, earning him the Nobel Prize in Physics in 1933, which he shared with Paul Dirac. But long before the honors came, Schrödinger already knew that he had changed the foundation of science. Wave mechanics did more than describe the atom, it transformed the entire architecture of physics. It provided the mathematical basis for the development of quantum chemistry, solid-state physics, and the emerging field of quantum computing nearly a century later. It showed that the invisible could be understood, not through pictures of particles colliding, but through the symphony of mathematical waves interacting in complex harmony. In this sense, Schrödinger's early fascination with mathematics found its ultimate expression in wave mechanics, a theory that revealed the universe as a vast composition of numbers and vibrations. And yet, even after this triumph, Schrödinger continued to reflect deeply on what his equation meant. He wrestled with the philosophical implications of his discovery, aware that it opened as many questions as it answered. What did it mean for a particle to be both localized and spread out as a wave? How could observation change the very nature of what was being observed? These were not merely technical puzzles. They were challenges to the very definition of reality. Schrödinger knew that his work had not just solved a problem in physics, it had transformed the way humanity perceives existence itself. The success of Schrödinger's wave mechanics did not mark an ending, it was the beginning of a new era. The publication of his equation spread like a spark through the laboratories and lecture halls of Europe, igniting an intellectual revolution. Physicists who had struggled to reconcile the dual nature of matter now possessed a language that could unite wave and particle within one coherent vision. The love function, the wave function, became a symbol of this unity, a mathematical melody describing how matter behaved not as a collection of billiard balls, but as patterns of probability. The impact was immediate and unstoppable, and it reached far beyond physics alone. Yet Schrödinger himself never rested content with his success. He was a man of questions more than of answers, forever chasing the deeper meaning behind his own discoveries. To him, the triumph of wave mechanics was not simply a computational tool, it was a philosophical revelation. It hinted that the universe might be fundamentally continuous, that beneath the apparent randomness of atomic behavior lay a hidden order, a harmony woven from waves of possibility. He felt that his equation was not a map of chance, but a symphony of necessity. Every solution to his equation corresponded to a standing wave, a stable pattern that represented the possible states of a particle. The atom was no longer a chaotic jumble, but a resonant system, like a musical instrument producing discrete notes from the vibration of a single string. This image of resonance captured the imagination of the scientific world. It gave physicists a way to visualize what had once been purely abstract. They could now speak of orbitals, three-dimensional wave patterns that defined where electrons were likely to be found around the nucleus. These orbitals were not just mathematical curiosities, they could be pictured, drawn, and studied. Each had its own shape and energy, from simple spherical clouds to complex lobes and rings. Chemistry itself was reborn through this vision. The behavior of atoms in molecules, the structure of crystals, the color of minerals, all could now be traced back to the patterns of Schrödinger's waves. But even as his work revolutionized science, it also exposed the deep philosophical fissures within quantum theory. Schrödinger resisted the growing influence of the Copenhagen school, led by Niels Bohr and Werner Heisenberg, who interpreted quantum mechanics as a fundamentally probabilistic theory. To Bohr and his followers, the wave function did not describe an objective physical wave, but merely the knowledge or information we have about a system. When an observation was made, the wave function collapsed, selecting a single outcome from many possibilities. Schrödinger found this notion intolerable. He believed that physics should describe reality itself, not merely the limits of human observation. In letters and essays, he expressed his discomfort with what he called the quantum jump, the idea that particles could instantaneously change their state without any causal mechanism. It was as though nature played dice with itself, violating the smooth continuity he so cherished. Out of this philosophical tension would come one of the most famous thought experiments in the history of science, the paradox of Schrödinger's cat. Although he introduced it later as a critique of the Copenhagen view, its roots were already visible in his struggle to reconcile wave mechanics with reality. For Schrödinger, the cat paradox was not a celebration of quantum weirdness, but a protest against it. He continued to defend the view that the wave function represented something real and continuous. He dreamed of a wave picture, of the universe where particles were merely localized concentrations of energy in a vast ocean of waves. His contemporaries found this idea too classical, too intuitive for the new quantum age. But in many ways, Schrödinger was ahead of his time. Decades later, theories like quantum field theory and the pilot wave interpretation of David Bohm would echo his vision, treating particles as excitations or guided motions within underlying fields. What Schrödinger glimpsed intuitively in the 1920s would become a cornerstone of modern physics in the second half of the century. In his lectures and writings, Schrödinger often invoked imagery that blurred the line between physics and philosophy. He saw mathematics not as an abstract tool, but as the language of nature's soul. When he spoke of the wave function, he spoke of patterns that existed beyond perception, forms that gave rise to matter and energy alike. He felt that science and philosophy were not separate realms, but complementary reflections of the same quest for truth. This holistic view was deeply influenced by his reading of ancient thinkers, especially the Vedantic philosophy of India. He found in it an affirmation of the unity of all existence, a theme that resonated with his scientific belief in the interconnectedness of the universe. While his contemporaries debated the interpretation of quantum mechanics, Schrödinger pressed forward with applying wave mechanics to more complex systems. He developed methods to describe molecules, leading to the birth of quantum chemistry, Collaborating with other pioneers, he helped establish the mathematical foundations that would allow scientists to calculate bonding energies, molecular shapes, and reaction pathways. The modern understanding of chemical bonding, the reason water, carbon, and oxygen form the substances of life, owes much to Schrödinger's framework. Without it, the entire field of molecular science would still be groping in the dark. Yet for Schrödinger, success brought no peace. He felt increasingly isolated from the philosophical direction physics was taking. The probabilistic interpretation, championed by Bohr and Heisenberg, was gaining dominance. To many younger physicists, questions about the reality of the wave function seemed irrelevant. What mattered was that the theory worked. Schrödinger disagreed. To him, science was not just about prediction but understanding. He wanted to know what the world was truly made of, not merely how it behaved in experiments. In private correspondence, he lamented that physics had lost its soul, that the beauty of the world was being replaced by the cold logic of measurement. Even as he grew disillusioned with certain interpretations, Schrödinger's influence deepened. His equation became the foundation upon which later generations would build the edifice of quantum theory. In solid-state physics, it explained how electrons move through crystals, giving rise to semiconductors and ultimately to the computer age. In nuclear physics, it guided the understanding of particle interactions and energy levels. In astrophysics, it helped describe the behavior of matter under extreme conditions inside stars. And in the emerging field of quantum information, his ideas continue to shape how scientists think about computation and entanglement. Every laser beam, transistor, and microchip in today's world carries the mathematical signature of Schrödinger's wave mechanics. Perhaps the most poetic aspect of his legacy is that Schrödinger's equation describes both matter and mind in unexpected ways. In later years, he turned his attention to biology, seeking a unifying principle that could explain life in the same way wave mechanics explained atoms. His 1944 book, What is Life?, inspired a generation of biologists, including James Watson and Francis Crick, who would go on to discover the structure of DNA. Schrödinger's vision of life as an ordered system governed by the laws of physics became one of the bridges between quantum theory and the study of living systems. Though his wave equation was born in the world of atoms, its spirit reached into the mystery of consciousness and existence itself. Reflecting on his career, one senses that Schrödinger was not merely a scientist but a seeker, a philosopher who used equations as his verses and the universe as his manuscript. He never saw physics as a collection of dry facts. To him it was a living poem written in mathematical language. Each symbol, each variable in his equation carried the rhythm of a deeper truth. When he looked at he did not see a formula, but a metaphor for being itself. The universe, he believed, was not made of separate things but of interconnected patterns of energy and awareness. His contemporaries sometimes mocked his philosophical inclinations, but Schrödinger's synthesis of science and spirituality proved enduring. In the decades that followed, as quantum physics continued to evolve, his equation remained unshaken. Experimental verification after verification confirmed its accuracy. The electrons in atoms behaved precisely as his waves predicted. The colors of elements, the shapes of molecules, the tunneling of particles through barriers, all followed from the mathematics he had introduced in the 1920s. In a field known for constant upheaval, Schrödinger's equation became a rare island of permanence. It is astonishing to consider how much of our technological civilization rests upon the insight of a single mind seeking beauty in the patterns of nature. From the luminous displays of smartphones to the vast networks of satellites orbiting Earth, from the scanning, tunneling microscopes that image individual atoms to the algorithms of quantum computing that promise to redefine information itself, all depend on the principles he revealed. What began as a solitary search in the snowy silence of the Alps became the foundation for the modern world. But beyond technology, Schrödinger's wave mechanics changed humanity's philosophical understanding of existence. It taught us that certainty is an illusion, that the universe is not made of rigid, separable things but of relationships, probabilities, and interactions. Reality, in Schrödinger's view, is a tapestry woven from mathematical vibrations. The world we perceive as solid is a manifestation of underlying waves constantly interacting and interfering. This realization blurred the boundary between the observer and the observed, suggesting that consciousness itself might be entangled with the physical world it perceives. Though Schrödinger never claimed to have solved the mystery of mind, his writings hinted that the same unity governing matter might extend to awareness, a daring thought that continues to inspire physicists and philosophers alike. In his later years, Schrödinger lived quietly, teaching, writing, and reflecting. He had seen the world plunge into wars and rebuild itself with the help of technologies his work had made possible. He watched quantum theory grow from a small circle of European scientists into a global enterprise shaping the destiny of nations. Yet he remained modest about his achievements. In his lectures, he often reminded students that scientific discovery is not about domination over nature, but communion with it. To understand the universe, one must listen to its harmony, not impose one's will upon it. This humility, rare among great minds, made his influence not only intellectual but moral. The legacy of wave mechanics today extends far beyond laboratories. It has reshaped how we think about reality, causality, and knowledge. In philosophy, it challenged the classical notion of objective truth. In art and literature, it inspired metaphors of uncertainty and interconnection. In technology, it became the invisible architecture of progress. And in education, it continues to teach new generations that science is a dialogue between imagination and experiment, intuition and rigor. When physicists write Schrödinger's equation today, they are not merely manipulating symbols. They are invoking one of the most profound insights ever conceived by the human mind, that all matter, energy, and perhaps life itself are expressions of the same underlying mathematical order. The function that Schrödinger introduced almost a century ago continues to pulse at the heart of every scientific model that describes the subatomic world. It is the language of the electron, the song of the photon, the whisper of atoms as they form the building blocks of stars and souls alike. If the 20th century was the age of relativity and quantum theory, then Schrödinger's contribution gave it its melody. His wave mechanics harmonized the chaos of the microscopic realm into something comprehensible, something almost lyrical. He revealed that even in the apparent randomness of particles, there exists a hidden rhythm. A rhythm that connects everything that is, was, and ever will be. In doing so, he not only laid the foundation of modern quantum physics, but also gave humanity a new way to imagine itself within the cosmos. Not as an outsider observing from afar, but as part of the very wave that sustains existence. Thus, the genius who gave life to the quantum cat also gave voice to the universe itself. His equation, simple yet infinite in its reach, continues to unfold in every scientific discovery, every technological innovation, and every philosophical reflection on what it means to exist. Erwin Schrödinger's wave mechanics was more than a breakthrough in physics. It was a revelation of unity, a bridge between the tangible and the abstract, between science and art, between knowledge and wonder. And as long as humanity continues to explore the mysteries of the quantum world, the echoes of his waves will never fade. At the dawn of the 20th century, the world of physics stood divided. On one side was the well-ordered universe of classical mechanics, a cosmos governed by predictable laws, a place where motion, force, and energy obeyed the logic of Isaac Newton and James Clerk Maxwell. On the other side loomed a growing mystery, the quantum realm, where certainty dissolved into probability and matter behaved in ways that defied intuition. The gap between these two worlds was not merely scientific, it was philosophical. It represented a fracture in humanity's understanding of nature itself. And it was across this chasm that Erwin Schrödinger built his bridge. His wave mechanics did not simply describe new equations, It offered a language that united the determinism of classical thought with the uncertainty of the quantum domain, giving coherence to a world that seemed to have lost its meaning. Schrödinger was not born into chaos. His intellectual upbringing had steeped him in the harmony of classical physics. From his early years in Vienna, he absorbed the teachings of mechanics, electromagnetism, and thermodynamics. He revered the symmetry of Maxwell's equations and the clarity of Newton's laws. To him, science was not just a system of calculations. It was an expression of order, beauty, and reason. This early devotion to the ideals of classical physics would later shape his deepest struggles with quantum theory. When the new physics began to emerge, tearing apart the old certainties, Schrödinger felt compelled not to reject it but to reconcile it with the elegance he so admired. The early decades of the 20th century were filled with astonishing discoveries that exposed the limitations of classical thinking. Planck's quantization of energy, Einstein's photoelectric effect, and Bohr's atomic model all hinted at a hidden structure beneath reality, a structure that refused to obey the smooth predictability of Newtonian motion. Experiments showed that light could behave like particles and electrons could behave like waves. The world was no longer one of solid matter and definite paths, but of paradoxes and probabilities. For many scientists, this transformation was exhilarating. For Schrödinger, it was unsettling. He sensed that something essential had been lost, a vision of unity that had guided science for centuries. His life's mission became to find that unity again, to weave together the threads of the old and the new into a single coherent tapestry. When he read Louis de Broglie's thesis in 1924, proposing that matter could have wave-like properties, it was as though the first plank of that bridge appeared before him. Here was an idea that could connect the particle world of Newton to the wave world of Maxwell. De Broglie's matter waves offered a conceptual link between the tangible and the abstract, between mechanics and electromagnetism. To Schrödinger, this was not merely a new hypothesis, it was a revelation. He realized that if particles such as electrons could be described by waves, then perhaps the deterministic laws of classical physics could be extended into the quantum realm, not discarded but reborn in a new form. For months he labored to turn this vision into mathematics, drawing upon the equations that described vibrating strings and the propagation of light. He sought an expression that could govern matter waves. The result, born from this synthesis, was the Schrödinger equation, a masterpiece that embodied the bridge he dreamed of. On one side, it resembled the wave equations of classical physics. On the other, it revealed the probabilistic essence of quantum behavior. It was both familiar and revolutionary, a fusion of old concepts and new realities. With a single elegant formula, Schrödinger transformed the chaos of quantum phenomena into an ordered framework that resonated with the logic of classical thought. When he first presented his work to the scientific community, it seemed almost too beautiful to be true. The same mathematical methods that had once described sound and light now revealed the architecture of atoms. His equation predicted the energy levels of the hydrogen atom with breathtaking accuracy, confirming the quantized structure that Bohr had postulated but could not fully explain. Suddenly, the strange jumps of electrons between orbits were no longer mystical. They emerged naturally from the continuous waves of Schrödinger's theory. The bridge was complete. Quantum discontinuity had been translated into classical continuity through the language of mathematics. Schrödinger's wave mechanics gave physicists a vision they could grasp. The atom, once an enigma of invisible orbits, became a stage upon which waves danced in harmonious patterns. Each electron was a standing wave, vibrating within the potential of the atomic nucleus, its shape defined by the boundaries of space and energy. These waves could interfere, combine, and evolve, just as light waves did in the macroscopic world. In this way, Schrödinger restored to quantum theory a sense of visual and conceptual coherence. Where Heisenberg's matrix mechanics seemed abstract and inaccessible, Schrödinger's waves spoke in the familiar language of classical physics. inviting both intuition and imagination. And yet, this bridge was more than a technical achievement. It was a philosophical reconciliation. It brought together two worldviews that had seemed irreconcilable: the deterministic vision of Laplace's clockwork universe and the probabilistic vision emerging from the experiments of the new century. Schrödinger's equation preserved the determinism of evolution. The wave function evolves according to precise laws, while simultaneously embracing the quantum idea that measurement reveals only probabilities. It was as though he had built a bridge of light between the past and the future, between the certainty of cause and the mystery of chance. But no bridge exists without tension. Schrödinger's own relationship with quantum theory remained conflicted. While his equation connected the two worlds, he himself struggled with what it implied. The probabilistic interpretation advanced by Max Born and Niels Bohr suggested that his beautiful waves did not represent real, physical oscillations, but merely the mathematical description of likelihoods. Schrödinger resisted this view with all his intellectual passion. To him, the wave function was real, something that existed independently of observation. He saw in it the possibility of a unified reality that transcended the dualism of particles and waves. He wanted the bridge to be built of substance, not shadows. In his letters and papers, Schrödinger often expressed his discomfort with the idea that the observer could shape reality. He wanted physics to describe what is, not just what is measured. This philosophical struggle added depth to his scientific journey, transforming it from mere problem-solving into a quest for truth. His bridge between classical and quantum physics was not only mathematical but existential. It was an attempt to reconcile two ways of understanding the world: the external and the internal, the mechanical and the metaphysical. The elegance of his theory drew admiration from contemporaries such as Einstein, who shared his longing for a deterministic universe. Einstein famously wrote that Schrödinger's work captured the soul of physics, though he too rejected the growing probabilistic interpretation. Together they stood as guardians of a vanishing ideal, that nature at its core must be rational and continuous. Their correspondence reveals not only scientific debate but deep mutual respect, united by a shared conviction that truth must possess beauty. Schrödinger's wave mechanics thus served as the bridge across which Einstein's relativity and Bohr's quantum theory could begin to communicate. Relativity described the universe of the large, governed by geometry and space-time. Quantum mechanics ruled the world of the small, ruled by probabilities. Schrödinger's equation, with its elegant balance of determinism and uncertainty, stood at the intersection. It allowed scientists to apply classical techniques, differential equations, energy conservation, boundary conditions, to phenomena that were fundamentally quantum. It was as if he had translated the new language of the microscopic into the ancient grammar of motion. The implications were immense. Through wave mechanics, physicists could calculate the energy of electrons in atoms and molecules, predict chemical bonds, and explain why matter was stable at all. They could see, for the first time, that the same mathematical principles governing the ripples on a pond also governed the behavior of the tiniest particles of the universe. This unity, hidden for centuries, was now revealed. Schrödinger had not only built a bridge, he had illuminated the path toward a deeper understanding of reality itself. His achievement also transformed education and thought. Students who once studied Newton's laws as separate from atomic physics could now see them as connected parts of a greater whole. The wave equation became a universal tool, linking the mechanics of the visible world with the mysteries of the invisible. Generations of scientists would grow up traversing Schrödinger's bridge, moving effortlessly between the classical and the quantum, guided by the same mathematical rhythm. It is difficult to overstate the cultural significance of this synthesis. At a time when the world itself was fractured by war and uncertainty, Schrödinger's work represented a triumph of reason over fragmentation. His wave mechanics suggested that order could emerge from chaos, that even the most counterintuitive phenomena could be woven into a coherent narrative. The bridge he built between the old and new worlds of physics was also a metaphor for humanity's enduring quest for meaning in an age of uncertainty. To stand on that bridge is to feel the flow of history beneath one's feet. The classical world of Galileo and Newton on one side, the quantum world of Bohr and Heisenberg on the other, and Schrödinger's luminous wave passing between them like a current of understanding. The equations that emerged from his mind were not mere symbols, they were stepping stones across the abyss of confusion that had opened in the early 20th century. And on those stones, science found its balance once more. Even the act of calculation in wave mechanics feels like crossing that bridge. When a physicist solves Schrödinger's equation, they begin with the deterministic logic of classical mathematics and end with the probabilistic truth of quantum outcomes. Each step of the derivation mirrors the journey of physics itself, from certainty to uncertainty, from simplicity to complexity, from the concrete to the abstract. Schrödinger's genius lay in creating a framework where this transformation could occur without breaking the continuity of understanding. And yet, Schrödinger himself knew that the bridge was not perfect. Beneath its graceful arches ran currents of paradox that could not be ignored. The collapse of the wave function during measurement, the apparent role of consciousness in defining outcomes, the strange phenomena of entanglement, all these hinted that the connection between the classical and quantum worlds was deeper and more mysterious than even he had imagined. But unlike many of his contemporaries, Schrödinger embraced this mystery not as a failure, but as an invitation. To him, science was not about closing doors but opening them, to the infinite complexity of nature and the boundless creativity of the human mind. Thus, his wave mechanics became more than a scientific tool, it became a philosophy of unity. It taught that the world could be both particle and wave, both deterministic and probabilistic, both measurable and unknowable. In the ripples of his equations, Schrödinger glimpsed a truth that transcended physics, that opposites are not enemies but complements, that the universe achieves harmony through tension, not resolution. His bridge between classical and quantum physics was therefore not just a structure of logic but a symbol of synthesis, a reminder that progress arises when contradictions are embraced, not erased. By the time his work was fully recognized, Schrödinger had already changed the intellectual landscape forever. The divide that once separated Newton's apple from the quantum atom had been crossed. The path he forged allowed later generations to expand physics into new territories, quantum fields, condensed matter, molecular dynamics, and beyond. His bridge did not end where he stopped, it extended forward, evolving with every new discovery, carrying science ever closer to the elusive dream of a unified theory. The idea behind Schrödinger's cat was not to confuse or amuse. It was meant to provoke the mind into confronting the uncomfortable truth at the heart of quantum mechanics. In the microscopic world, particles behave as if they can exist in multiple states at once, a concept known as superposition. To explain this strange reality, Schrödinger built his thought experiment around a simple but powerful story: a cat, a sealed box, a vial of poison, and a radioactive atom that could decay at any moment. If the atom decayed, the poison would be released and the cat would die. If it did not decay, the cat would live. But here was the strange twist according to quantum mechanics: until the box is opened and an observation is made, the cat exists in both states simultaneously, alive and dead at once. It was not the fate of the cat that mattered most, but the deeper message hidden inside the box. The message that reality itself might not exist in one definite form until we look at it. Schrödinger used this story to expose the philosophical tension that had been building in quantum physics since the days of Niels Bohr and Werner Heisenberg. Bohr and Heisenberg's Copenhagen interpretation claimed that the act of observation plays a central role in determining physical reality. Schrödinger found this deeply unsettling. He believed that the world must exist independently of human observation. His cat paradox was meant as a critique, a warning that quantum theory, if taken literally, leads to absurd conclusions. Yet ironically, it became the most famous symbol of the quantum world, a metaphor so powerful that even today, decades later, it continues to appear in science, art, and philosophy. The cat in the box became more than a scientific thought experiment. It became a mirror reflecting humanity's struggle to grasp the strange laws that govern the unseen. It forced physicists and philosophers alike to question what it means to know something. Before quantum theory, the world seemed predictable and solid. The laws of Newton told us that if we knew the position and velocity of every particle, we could predict the future with perfect certainty. But Schrödinger's cat shattered that comfortable view. It revealed a universe where uncertainty is not just a limitation of knowledge, it is a fundamental property of reality itself. As the thought experiment spread through academic circles, it sparked fierce debate. Some scientists dismissed it as philosophical nonsense, while others embraced it as a profound insight into the mystery of measurement. The idea of a cat being alive and dead at once seemed impossible, yet experiments in later decades began to show that the quantum world really does behave that way. Particles can exist in multiple states simultaneously, and only when they are observed do they collapse into one outcome. What Schrödinger once used to highlight absurdity became a roadmap to deeper understanding. The paradox he introduced would go on to inspire entire branches of physics, from quantum computing to quantum entanglement research. Over time, Schrödinger's cat grew beyond its scientific roots. It entered the public imagination as a symbol of ambiguity, mystery, and duality. Artists, writers, and filmmakers used it to explore the boundaries between life and death, perception and reality, existence and non-existence. In classrooms across the world, the story became a gateway for students to enter the strange world of quantum theory. Even though Schrödinger himself disliked the popularization of the cat, it became his most enduring legacy. Through this one image, he captured the essence of quantum uncertainty more powerfully than any equation ever could. Yet behind the brilliance of the thought experiment lay a man deeply troubled by its implications. Schrödinger's writings reveal a mind torn between logic and wonder. He admired the mathematical precision of physics, but struggled with its philosophical consequences. The idea that observation could shape reality disturbed him. He feared that science might be losing its connection to an objective world. But even as he challenged the quantum orthodoxy, he recognized that the universe was more mysterious than human reason could easily explain. His cat was not just a scientific symbol. It was a reflection of his inner struggle, a metaphor for the balance between reason and imagination. In the decades following Schrödinger's proposal, scientists continued to test the strange predictions of quantum mechanics. What they found only deepened the mystery. Experiments confirmed that particles can exist in superpositions, that they can be entangled across space, and that observation truly plays a role in determining outcomes. The philosophical question that Schrödinger raised, what is reality before we look at it, remains unanswered. In this sense, the cat in the box still waits, suspended between two worlds, challenging humanity to keep questioning the boundaries of knowledge. Schrödinger's cat also pushed scientists to think about the limits of human perception. Our senses evolved to navigate a macroscopic world of solid objects, not the ghostly realm of atoms and waves. The thought experiment reminded us that the quantum world does not obey the same logic as our everyday experience. It follows its own rules. Where particles can be waves, outcomes can be probabilities, and existence itself seems to depend on interaction. The cat's strange fate forced scientists to realize that the universe is not built upon certainty, but upon possibility. The influence of this single idea stretched far beyond physics. Philosophers used it to explore consciousness and the nature of reality. Psychologists compared it to the duality of the human mind, the coexistence of reason and emotion, belief and doubt. Even theologians found in it echoes of ancient paradoxes about existence and non-existence. In the modern era, The cat became a cultural icon of quantum weirdness, appearing in novels, television, and art. It symbolized not only the complexity of science, but also the endless curiosity that drives the human spirit. Schrödinger's cat endures because it captures something timeless about the search for truth. It shows that the pursuit of knowledge is not always about answers. It is often about the courage to face uncertainty. Schrödinger may have designed the cat to criticize quantum mechanics, but in doing so, he revealed its deepest beauty. The cat lives in the imagination of every thinker who dares to open the box and look inside, knowing that what they find might change their understanding of reality forever. Erwin Schrödinger's thought experiment stands as one of the most remarkable intellectual creations of the 20th century. It was not born in a laboratory or tested with instruments, but forged in the power of pure thought. It bridged science and philosophy, reason and wonder, the measurable and the unknowable. The cat's paradox is a reminder that every discovery carries within it a question, and every answer opens the door to a new mystery. Schrödinger gave life to a symbol that transcends time, a symbol that whispers to us about the fragile boundary between knowledge and imagination. In the end, the quantum cat is not just about physics, it is about us. It reminds humanity that our understanding of the universe is still incomplete, that reality may be more complex than we can ever grasp, and that curiosity is the most powerful force we possess. Through his playful yet profound idea, Schrödinger transformed the way we see the microscopic world, and perhaps the way we see ourselves. Even today, as scientists probe deeper into the quantum realm, the cat remains there, half in shadow, half in light, waiting to be observed, waiting to reveal yet another truth about the strange and beautiful nature of existence. Erwin Schrödinger was not just a physicist confined to formulas and experiments, he was a philosopher of nature, a thinker who looked beyond the numbers to search for meaning in the patterns of the universe. His mind worked at the intersection of science and philosophy, where logic met imagination and reason blended with wonder. For Schrödinger, understanding the universe was not only about discovering its laws, but also about understanding humanity's place within those laws. He saw science as a language that could describe not only the movements of atoms, but also the essence of life itself. Throughout his career, Schrödinger refused to separate the scientific from the philosophical. He believed that physics, when stripped of its connection to human experience, loses its soul. His fascination with the mystery of existence led him to ask questions that most scientists avoided. What is life? What is consciousness? What connects the material world with the awareness that observes it? These were not just abstract curiosities for him, they were central to his understanding of quantum theory and reality itself. In a time when most of his peers focused on equations and experiments, Schrödinger dared to question the very nature of being. His approach to quantum mechanics reflected this philosophy. While other scientists treated the wave function as a purely mathematical construct, Schrödinger saw it as a bridge between the world of matter and the world of perception. He believed that the beauty of science lies in its unity, that the same principles guiding the movement of electrons might also explain the rhythm of life and the harmony of consciousness. This view set him apart from the rigid materialism of his era. He saw the universe not as a cold machine, but as a living whole, a continuous, dynamic field where everything was interconnected. This idea became even more profound in his later years, when he turned his attention toward biology and philosophy. In his famous book, What is Life?, Schrödinger explored how the laws of physics and chemistry could give rise to the complexity and order of living organisms. He proposed that life must obey the principles of physics, but in a way that preserves information across generations, an idea that later inspired the discovery of DNA. His reflections in that book bridged the gap between the physical and biological sciences, showing that understanding the universe also meant understanding ourselves. What made Schrödinger truly unique was his conviction that knowledge and spirituality were not enemies but companions. He drew inspiration from ancient Eastern philosophies, especially the Vedanta tradition, which taught that all existence is one and that separation is an illusion. Schrödinger saw a deep resonance between these spiritual ideas and the discoveries of quantum mechanics. Just as quantum theory revealed the interconnectedness of all particles, philosophy revealed the unity of all life. In this way, Schrödinger's thinking transcended science. It became a meditation on existence itself. He believed that the human mind was not just an observer of the universe, but an active participant in it. The mystery of consciousness, to him, was not something that could be reduced to physical processes alone. He argued that awareness was a fundamental aspect of reality, intertwined with the very fabric of nature. This view challenged the purely materialistic worldview of his time and opened new discussions about the role of the observer in science. Schrödinger's deep interest in philosophy allowed him to explore the limits of scientific explanation and to acknowledge that not everything can be captured by equations. His writings carried a poetic tone that revealed the depth of his reflections. He wrote about the unity of all being, the illusion of separateness, and the eternal cycle of life and death. In these thoughts, he found harmony between science and spirituality, between knowledge and mystery. To him, the search for truth was not just a technical endeavor, but a moral and philosophical journey. The same curiosity that led him to formulate wave mechanics also drove him to question the purpose of existence. In the end, Schrödinger's philosophical approach gave physics a soul. He reminded the world that science is not only about discovering what is measurable, but also about seeking meaning in what is immeasurable. His ideas bridged two worlds, the world of logic and the world of wonder. He showed that to understand reality, one must also understand oneself, because the observer and the observed are part of the same cosmic dance. Through his life and work, Schrödinger became a symbol of unity between reason and intuition, demonstrating that true genius lies not only in solving equations, but in understanding the mystery behind them. His philosophy continues to inspire scientists, thinkers, and dreamers to look beyond the surface of things and to seek the deeper truth that connects all forms of existence. When Erwin Schrödinger formulated his equation, he unknowingly gave the world one of the most powerful tools in modern physics, a key that would unlock the invisible structure of reality itself. The Schrödinger equation was not just a mathematical achievement. It was a revelation, a new language to describe the unseen motions of the quantum world. Before him, scientists struggled to understand how particles behaved on the smallest scales. The laws of classical mechanics worked perfectly for planets and projectiles, but they failed in the realm of atoms and electrons. Schrödinger dared to imagine a new kind of mechanics, one based not on solid orbits but on waves of probability, waves that captured the mysterious dual nature of matter. In 1926, as he developed this theory, Schrödinger discovered that particles could be described not as tiny points moving along fixed paths, but as wave functions that spread through space, defining where a particle could possibly be. His equation mathematically linked energy, motion, and probability, revealing that the behavior of every particle could be predicted, not precisely, but through a range of possibilities. This was a radical departure from the certainty of Newton's world. Suddenly, reality was no longer solid and predictable, it was fluid, dynamic, and probabilistic. The universe itself seemed to hum with hidden waves, unseen yet deeply real. The Schrödinger equation soon became one of the central pillars of quantum mechanics. It described how the wave function of a particle evolves with time, how atoms form, how light interacts with matter, and even how the universe holds together on the smallest scales. It was this equation that allowed scientists to explain the structure of the hydrogen atom, predict the behavior of electrons, and understand the chemical bonds that make up all life. Without it, modern chemistry, electronics, and even quantum computing would not exist. Schrödinger's mathematical insight had transformed the landscape of physics forever. What made this achievement even more remarkable was that it came not from an experimental discovery, but from pure thought. Schrödinger built his ideas from mathematical reasoning and imagination, driven by the belief that beauty and simplicity guide truth. He once said that his equation came to him during a period of intense solitude in the Swiss Alps, where he worked in quiet isolation, following his intuition. The result of that period was an equation that captured the very heartbeat of the quantum world. It was elegant and universal, describing both the smallest particles and the largest systems that obey quantum laws. The equation's impact went far beyond physics. It changed how humanity viewed reality itself. If everything at its core was governed by probabilities, then certainty was an illusion. The equation suggested that the universe operates on possibilities, and that observation plays a role in shaping outcomes. This idea reshaped philosophy, challenging the notion of an objective, detached reality. The deterministic clockwork universe of the 19th century gave way to a probabilistic cosmos, where chance and observation intertwined in ways that defied classical understanding. Schrödinger's equation became the foundation upon which countless discoveries were built. It explained how atoms absorb and emit light, leading to the development of lasers. It described the motion of electrons in metals, paving the way for semiconductors and computers. It even inspired new theories of matter and energy that would later form the basis of modern technology. Every quantum device, from MRI machines to microchips, carries within it the spirit of Schrödinger's insight. His equation became not only a formula on paper, but a living force that reshaped civilization. Yet for Schrödinger, the equation was more than just a tool. He saw it as a glimpse into the unity of nature, a mathematical expression of how all things are connected by waves of energy. It was a reflection of his lifelong belief that the universe is not a collection of separate parts, but a single, flowing whole. In the rhythm of his equation, he found harmony between science and philosophy, between matter and spirit. The wave function, to him, was not merely a mathematical abstraction, it was the pulse of existence itself, the invisible thread that binds every particle, every atom, and every living being together. As time passed, physicists continued to expand on Schrödinger's work, finding new interpretations and applications. Some, like Heisenberg, focused on uncertainty and measurement, while others explored the wave-particle duality that Schrödinger's ideas illuminated. But no matter how the field evolved, his equation remained its foundation. Even now, nearly a century later, every student of quantum mechanics begins their journey with it. The Schrödinger equation stands as a monument to human intellect, a symbol of how imagination and mathematics can reveal the secrets of the cosmos. In the story of science, few ideas have had such profound and lasting influence. Schrödinger's equation turned chaos into clarity, transforming mystery into understanding. It showed that even in the randomness of quantum behavior, there is a deep and beautiful order, a harmony hidden beneath the surface of uncertainty. Through his equation, Schrödinger gave the world a way to see the unseen, to predict the unpredictable, and to find structure in the strange dance of particles and waves. His work was not just a step forward in physics, it was a leap in human understanding, a reminder that even the most mysterious corners of the universe can be illuminated by the light of thought. Erwin Schrödinger's mind was one that refused to be confined within the walls of a single discipline. His influence extended far beyond physics, reaching into biology, philosophy, and even the study of consciousness. What made his genius so remarkable was his ability to see the connections between seemingly unrelated fields, and to recognize that the laws of nature governing atoms and waves might also reveal the secrets of life itself. Schrödinger was not satisfied with understanding how matter behaves, he wanted to know what drives existence, what creates order in a universe that constantly tends toward chaos. This thirst for unity between science and life led him to write one of the most visionary works of the 20th century. What is Life? A book that changed the course of modern biology and bridged the gap between the physical and the living worlds. In this remarkable work, Schrödinger explored a profound question: How can living organisms maintain structure, order, and identity despite the constant tendency of matter to decay and disorder? Physics, at the time, was the science of the inanimate, the study of objects that followed predictable laws. Life, however, seemed to defy those laws. Living beings resisted entropy, the natural drift toward chaos. Schrödinger proposed that life achieves this by feeding on what he called negative entropy, but drawing order from the environment to sustain itself. This insight was revolutionary, laying the groundwork for the understanding of how energy flows through biological systems and how information is preserved within the complex patterns of living matter. But Schrödinger's greatest contribution to biology went even deeper. He speculated that the secret of heredity, the way traits are passed from one generation to the next, must lie in a stable molecular structure capable of storing information. He described this structure as an aperiodic crystal, a molecule with an ordered yet complex arrangement that could carry a genetic code. Remarkably, this idea anticipated the discovery of DNA by nearly a decade. The double helix structure of DNA, uncovered later by Watson and Crick, fit almost perfectly with Schrödinger's theoretical vision. His thinking had guided them, and many others, toward one of the greatest scientific discoveries in history. Schrödinger's influence was not limited to biology. His reflections also transformed philosophy. He saw science not as a collection of isolated facts, but as a living dialogue between mind and nature. He was fascinated by the mystery of consciousness, by the fact that the universe is not only observed, but also aware of itself through human thought. He asked questions that went beyond the boundaries of physics. What is the nature of awareness? How can subjective experience arise from physical processes? Is the mind separate from the world it perceives, or is it part of the same continuum? For Schrödinger, consciousness was not an accidental byproduct of matter, but a fundamental aspect of existence. He believed that the observer and the observed were deeply connected, that reality was a unified whole in which mind and matter reflected one another. This belief drew him toward the ancient philosophies of the East. Schrödinger found in Vedanta, a school of Indian philosophy, a vision of reality that resonated deeply with his own. Vedanta taught that all existence is one, that individual consciousness is not separate from the universal consciousness, but rather a fragment of it. Schrödinger saw in this idea a harmony with quantum physics, where the boundaries between particles blur and everything is connected through invisible waves of energy. He often wrote about the illusion of separateness, suggesting that the distinction between self and world is only a mental construct. For him, science and spirituality were not enemies but partners in the search for truth. His work inspired generations of thinkers to look at science as something more than data and measurement. It became a way to explore the meaning of life and the unity of all existence. The impact of his ideas can be seen not only in the laboratories of physicists and biologists, but also in the reflections of philosophers and psychologists who seek to understand the human condition. Schrödinger taught that knowledge without wonder is empty, and that science without philosophy risks losing its connection to the greater mysteries of being. Through his cross-disciplinary thinking, Schrödinger helped shape a new way of understanding nature, one that sees life as a continuation of the same physical principles that govern the stars. His ideas bridged gaps between the sciences and the humanities, between the measurable and the meaningful. Even today, as quantum physics merges with neuroscience and artificial intelligence, the echoes of Schrödinger's thought can still be heard. He showed that curiosity should never stop at the boundary of one field, because truth itself is universal. In his writings and teachings, Schrödinger left behind more than theories. He left a vision. He showed that the same mathematical beauty that describes electrons can also describe the patterns of living cells, and that the same wonder that drives science also fuels the human spirit. His legacy is not only in the equations that bear his name, but in the way he expanded our understanding of what it means to be alive, to think, and to exist. He reminded the world that science, at its highest level, is not just about discovering how things work, but about uncovering why they exist at all. Through his boundless curiosity and philosophical depth, Erwin Schrödinger became a bridge between the material and the spiritual, between knowledge and meaning, a thinker whose influence continues to illuminate the path of discovery across the frontiers of science and the mysteries of life itself. Erwin Schrödinger's legacy is one that transcends the limits of time and discipline. His work reshaped the very foundation of modern science and continues to inspire generations of thinkers, scientists, and dreamers. Though he lived in an era of immense scientific transformation, his ideas reached beyond the laboratory and into the realm of philosophy, art, and imagination. Schrödinger's name became a symbol of curiosity, of a mind that dared to question not only how the universe works, but also what it means to exist within it. His influence did not end with the quantum revolution. It continues to shape the way we explore nature, understand consciousness, and define the boundaries of knowledge itself. Schrödinger's greatest legacy lies in his ability to merge the precision of science with the depth of philosophy. He never believed that physics was merely about numbers or experiments. To him, it was about unveiling the hidden patterns of reality. His work on wave mechanics opened a new door to understanding the behavior of matter on the smallest scales, but it also revealed something far greater: the profound interconnectedness of all things. Every particle, every wave, every flicker of energy was part of a grand, unified design. This idea inspired generations of physicists to continue probing the mysteries of the quantum world, leading to discoveries that define our modern age, from quantum computers to the understanding of atomic structure. Yet Schrödinger's legacy is not confined to equations. He influenced the spirit of scientific inquiry itself. His thought experiment, the famous Schrödinger's cat, became one of the most enduring metaphors in the history of science. A symbol of uncertainty, possibility, and the strange dance between reality and observation. Even today, the cat remains alive in our imagination, reminding us that science is not always about finding answers, but about asking the right questions. It challenges our assumptions about what is real and what is only a projection of our perception. Through that single idea, Schrödinger turned the act of observation into a philosophical reflection on existence itself. The influence of Schrödinger's thinking extended deeply into other fields. His book, What is Life?, planted the seeds of molecular biology, inspiring scientists like Watson and Crick to discover the structure of DNA. In that book, he proposed that the secret of life lies in the transfer of information, an idea that became one of the cornerstones of modern genetics and information theory. His vision connected physics, biology, and philosophy into one continuous narrative, showing that life is not separate from the physical universe, but a natural expression of its laws. Schrödinger's insight revealed that to understand life, one must understand the principles of order, energy, and information, the same forces that govern the stars and the atoms. His influence reached into the realm of thought itself. Philosophers and psychologists drew from his ideas about consciousness and reality. Schrödinger argued that the mind and the world are not two separate entities, but parts of a single, unified experience. This perspective resonated with ancient philosophies, particularly those from the East, such as Vedanta, which taught that all consciousness is one. By bringing together modern physics and timeless wisdom, Schrödinger bridged the gap between science and spirituality. He showed that the pursuit of knowledge is not merely about mastering the external world, but also about understanding the self that perceives it. Generations of scientists who followed in Schrödinger's footsteps found inspiration in his fearless curiosity. His willingness to think beyond conventional boundaries paved the way for new revolutions in quantum theory, cosmology, and even artificial intelligence. The spirit of exploration that defined his life continues to fuel modern science. Every new discovery in quantum entanglement, every step toward quantum computing, every question about consciousness echoes Schrödinger's vision. the belief that the universe is far more mysterious and interconnected than we can imagine. Beyond his scientific contributions, Schrödinger's legacy endures in the way he humanized science. He reminded the world that scientific progress must always remain connected to philosophy, ethics, and wonder. He once said that the task of science is not only to understand the world, but to awaken a sense of unity with it. For him, knowledge was not about control, it was about harmony. This view stands as a powerful counterbalance to the modern world's obsession with technology and power. Schrödinger's writings remind us that science is at its best when it is guided by curiosity, humility, and reverence for the mysteries it seeks to uncover. Even after his death in 1961, Schrödinger's influence has only grown. His ideas continue to shape the fields of quantum physics, molecular biology, neuroscience, and philosophy. The tools of modern science, from particle accelerators to quantum algorithms, are built upon the foundations he helped lay. But perhaps his most enduring contribution is not a formula or a theory, but a way of thinking, the courage to question reality, to blend science with imagination, and to see the universe as a living whole rather than a collection of separate parts. Erwin Schrödinger left behind more than discoveries. He left behind a vision of unity, curiosity, and endless exploration. His genius showed that the boundaries between disciplines, between science and art, between reason and wonder, are illusions created by human limitation. In the vastness of the cosmos, everything is connected, and to understand one part is to glimpse the whole. Schrödinger's legacy lives not just in laboratories and textbooks, but in the hearts of all who dare to ask the deeper questions. His life stands as a timeless reminder that true knowledge is not only about understanding the universe, it is about feeling at one with it.